Okay, morning everyone. Welcome back. Is there a cluster going on in your class? A lot of you got COVID. Not just asking. Okay. Um. Yeah, I found this letter. I'm not sure it's true or just a meme. I think quite funny, so I'll share it here. Any Q&A question from last week? Content tutorial? Any question you want to discuss? There will be a quiz going on the third hour. Okay, on the tutorial time later. Any question? Any question that you want to ask? That you don't understand, that you want to know? No? Okay, this week I have double student coming to the office hour, which is good. And they found out this law here that I did a mistake in my solution, but I will change it in the latest lecture notes. Because I distribute around all, which is the disjunction, you only allowed to distribute along n or n. Okay, it's like you distribute multiplication over the addition. Okay. You can only do associativity on double or double n, but you still can proceed once you distribute, and then you can use commutativity or associativity to prove it. But make sure you know that every step, what have I used? Okay. Make sure you check that. Someone asked me whether I will provide table in the exam or not. So I think I will only provide, if I provide, I will only provide the identities tables or the algebra or the algebras. I won't provide this one. You need to memorize, understand this. Okay. This, I mean, others can be derived from here. So you just need to know how to go from the conditional statement to and all statement. Okay, and then the double-headed arrow is just the implies Q and it converts. Okay, this two is enough for you to go through between disjunction and conditional. Okay. Okay. So, any other question? If not, we will go towards today's content. So today we will talk about proofs. Yeah, different type of proof. So, okay. So there's few terminology that I want to introduce first. So first of all is the axiom. So axiom is something that we assume to be true. May not necessarily exist, but we want those statements to be true. Okay. Only starting from axiom, we can prove some statement. We can make some statement and then prove it. And then we call it a theorem. Okay. We also call the theorem proposition when the theorem is somehow less important. And the step that you use to prove the theorem is called a proof. Okay. A valid argument that establishes the truth of a theorem. And then there's another word is lemma. Lemma is also a theorem, but usually lemma we refer to those that are proof to prove to be used to prove a theorem. Okay. So you prove the lemma first, and then you use the lemma to prove the theorem. And then after you prove the theorem, maybe some result will follow easily. We call it a corollary. Okay, so the chart is something like this. So maybe I draw it larger. Okay, before I draw the chart, let me introduce another word. It's the conjecture. Okay, conjecture is the statement that is that you think is true, but it's not proven. So, so the chart should be like this. So you gotta assume this is always true. Okay, and then you will reach like proposition. Okay, so you prove. Okay, got proposition, got lemma. Okay, and then this maybe can lead to theorem. Okay, theorem is something big that you want to know. And then maybe in practice, you do some calculation. You think that you try a few cases, you think that there's a statement to be true, but it's unproven. So only when proven is a theorem, but conjecture could be wrong as well, because it could be wrong as well. Maybe right, maybe true. Okay, maybe true. Okay. 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 So let's dive into the first proof. So okay, so let me set up the number first. So we will use proof in the number theory as an example for today. So let's see what the even number is. So an integer is even if there exists another integer such that n equals to 2k. Okay. And it's odd if there is a k in the integer such that n equals to 2k plus 1. Okay. So to convince you a bit, so I'll give you an example. For example, what is 8? What is 8? 8 is 2 to the power 2 times 4. Okay. So you can write it as 2 times a integer. About 1 minus about minus 11. It's 2 times 1. 2 times 1. Okay. 6 plus 1. Okay. Yeah. Okay. So this is what we assume to be true for now. Okay. So let's see. So the first thing we do is prove. And let's do an example, and then I will talk about the general idea. So theorem, let m be an even integer, then m minus 1 is odd. Yeah, so proof. So if we already studied predicate logic last 2 weeks, so you should be able to apply it. It is equivalent to for every m in Z, m even implies m minus 1 odd. Okay. Okay, so what you need to do is you have an m, take an m, you want to show that m minus 1 is odd. Okay, so I write down the m. So take m to be an even integer. Okay, I write WTS want to show. want to show. So to show. Okay, maybe I write the full sentence first. So we want to show that m-1 is okay. So since m is odd, so you should start from what you have first, and then you this is your destination. You want to show that m-1 is odd. So start from where you have first. So first, not that m equals to 2k for some k by definition, right? Okay. So should I move up? Let me move up. Okay, so then you want to check m-1. Okay, so m-1 is 2k minus 1, right? But I said that an odd number is something 2 times an integer plus 1. But here is minus 1, right? So how should I argue that m-1 is an odd number? But abstract 2 from k. Okay, so become 2k minus 2 plus 2 plus 1. Then, okay. So you mean this? Is the same, right? Abstract 1 from k, right? Is this what you say? Yeah, so yeah. So yeah. So what you get is 2. Okay, and then what you get is 2 times k minus 1 plus 1. Yeah. So this is your this is another integer. Okay. Then so m minus 1 is oh, okay. Okay. And any question or not? Any question? Any question? For the back? Following? Okay. Then fine. You confused or not? Confused? Ask it. Oh, why abstract the two? Do you agree I can abstract the two first? Huh? Yeah. So I minus 2 plus 2, so I did nothing, right? Okay. So you agree I can take 2 out, right? Because once you take the 2 out, you can cancel with a minus 1. Okay. 2 minus 1 is plus 1, which is what you want. Okay. I don't want to take 4 out. I don't want to take 6 out. Too many. Okay. Because I just want plus 1. Okay. Can get it? Then. Okay. 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 So the general statement should be P implies Q. Okay. There's a P implies Q here. So and then I start from P and then I get Q. So I got P implies Q, I got P, and then I got Q. Wait, sorry. I should say I got P and then I got Q. I got P implies Q. Yeah. So I get P implies Q is true. Okay. So this is the direct proof. Okay. Okay, next. So next is a proof by contradiction. So let's see. So what's the proof by contradiction? Axiom. So this is axiom. I want it to be true. Maybe it can be proven, but we don't want to go into it today. So every integer is either odd or even. So this is an exclusive OR. So I cannot, one integer cannot be both even or odd and odd. Okay. Exclusive OR. So let's see theorem, the same theorem. Let m be an integer. Okay, then n minus 1 is odd. Okay, proof. Okay, when I give this example, right, you don't need to understand. You just follow what I'm saying first, and then you try to understand. Okay, don't stop when I'm giving this example because I'm just telling you there's one such thing, and then later I will tell you why it's valid. Why is it valid? Just follow, finish the example first, and then I'll tell you why this. In general, why this example work. Yeah. So suppose. So in the proof of contradiction, suppose m, wait, I left out even. So suppose m even. So I assume the assumption, okay, and the special thing is I also assume the result is wrong, okay, and n minus 1 is even, okay. So I start from there, then n minus 1 equals to 2k, right? Because I assume n minus 1 is even. So m equals to 2k plus 1, right? Which is 4. Okay. So I claim that m is even, but I prove that m is odd. Okay. So we reach a contradiction. Okay. This means this assumption is wrong. Okay. So m minus 1 has to be odd. So in general, what is going on here? So we also have a P implies Q statement here. Okay. So we assume P, we assume not Q. Okay. And then we reach not P. Okay. So this implies Q. Okay. So in total, what do we have? We have P implies Q. Okay. We got P. We got not Q. We got not P. Okay. And then we get not Q implies P and not P. Okay. So this part here, we already proved that this is always a contradiction. Okay. So this one is false. So since I want this implication to be true because this is how I get it, right? So if this implication is true, not Q has to be what imply true, what imply false is true. False. Only false implies false is true. So that means I can get Q. Okay. Okay. So from P I can get Q. Okay, this is the logic. But yeah, okay. But yeah, okay. Later we'll see again the contradiction proof in another example, and then we will try and see. So next proof by contrapositive. Okay. So theorem. exactly the same theorem. So let M be an even integer. Okay, then M minus 1 is odd. Okay. The difference of this proof is I don't assume the assumption anymore. Okay? I don't suppose this assumption anymore. I just assume the result is wrong. Okay. M minus 1 is even. Okay. And then we want to reach what we want to reach. We want to show that M is odd. Okay. So not Q implies not P. So let's see. So we have M minus 1 equals to 2K. Exactly the same step. Okay. So M equals to 2K plus 1, which is odd. Let's divide it. Okay. So I have P implies Q. Here, the statement that I wanted to prove, and then I start from not Q, and then implies not P. Okay, but P implies Q, and not Q implies not P are logically equivalent. So I just prove this one, then I proven this. Okay. Any question or not? Any question? Any question? No, then in summary, so I write a short summary first for these three proofs. So later, let's see again. So I write a small summary here. So we got a direct proof, and then we got a contradiction. And then we got a contra. Let's see, if okay. So direct proof, what you have is you get a P. So you assume P. Okay, okay. I wrote a different color here. So I assume P, I prove Q, and then I got P plus Q. So this is your assume, and this is your proof. Okay. In contradiction, you got P. Okay, you assume P, you assume not Q. Okay, and then you prove not P. Okay, so and then you reach not Q implies P, and then you get. So this is you assume, and then you assume two things, and then you prove this. Then ignore this. Okay, and then in contradiction, you have not Q. Okay, you assume not Q, and then you prove not P. And then you get not Q implies not P, which is P implies Q. So you proven P implies Q. Yeah. Any question? Any question? Any question? Any question? Maybe I'm going quite fast already. Teach 2 days the same thing. Any question? No. Any question? Hey, is Liang here? Liang, the sleeping guy. Liang, not here. They're not here. You're always the first guy who reached the class. They're not here. Okay. Any question? This sounds a question. I know you got a lot of questions. Huh? No, eh? No question? No. Okay. Okay, if no, then we proceed. So we proceed. We will prove this square root 2 thingy. So prove that square root 2 is irrational. And I think we talked about this a little bit. Our theorem square root 2 is irrational. Okay. Now, since we want to show it by contradiction, right? So we need to assume not Q. So we will assume the result is false. So suppose, what? Okay. Suppose square root 2 is rational. Okay. Then square root 2 is equal to a ratio of 2 integers. Okay. Moreover, we also, okay, n of course not equal 0. Moreover, we can assume that m and n have no common factor, right? Because we can just take 2 over 4 and then divide it out. For example, PG. Okay, just take the simplest form. And this is very important assumption here. Okay, let me pass this attendance first. Okay, yeah. Then what do I do? So I square both sides. So square both sides to get this. Okay. Hence, I get 2n squared equals to m squared. Okay. What does this mean? So m squared equals to 2 times some integer. M is even. Okay, very good. So it follows that m squared is even. Okay. But since m squared is even, m must be even. Okay. I want you to spend 2 minutes to think why this statement is true. You can discuss with your friends why this statement is true. How to prove this statement. Okay, I put this as a lemma. So why is this true? Why m squared is even, m must be even. How to prove? So how to prove? Now the proof. Okay, later you tell me. Okay, anyone have any idea how to prove? you know how to prove? Okay. Okay. Uh, but I start from m squared is even. Okay. How do you deduce that m is 2 to the sum n? Right? It's it's not going backward. Going from m squared to m. Anyone got any idea or not? Huh? Yeah. Any, you mean two? Can you talk a little bit? So 2 multiplied by y. No. My question is if m squared is even, why m is even? Yeah. Ah, okay. Okay. So, right, right here. Okay. Okay. I don't know why you changed my odd number definition to -1, but that's fine. You just put it back, okay, back, okay, back. Yeah. Yeah. Okay. So this is proven by actually contra positive. Yeah. So you use contra positive is easier to prove this statement. I think direct proof. I'm not sure there's a direct proof or not. Maybe it's hard. Okay. Mm, yeah. So I move the oh, so I move this up. Okay. So since m squared is even, m must be even. M must be even. So what is it? What does this mean? So m equals to 2a for some a. Okay, by lemma. The lemma approach. Okay, notice that I name it as a lemma because I want to prove the theorem. So in the meantime, I reach this difficulties. So then m squared is 4 to the a squared. Okay. Yeah. Okay. And so we have what 2n squared equal to 4n squared. Okay. And then we have s square equal to 2s squared. Repeat, right? Repeat again. So hence n squared is even. Okay, which implies n is even. Okay. So what we've done? So we proved that n is even. M is also even. Okay. Since both of them even, they are 2 to the sum, 2 times some integer, right? So, but I said that they have no common factor. So there's a contradiction. So there okay. Okay. I think there's a sleeping bug inside our room. Liang is not here, but different people sleep. Okay. Uh, okay, next. Any question on this proof? Yeah. Multiply two odd can produce an even. Yeah. What do you mean by obvious? It's going to what? So what did you use? How do you prove that statement? Yeah, this is how you prove that statement. What longer method for? You mean every? You mean every? You mean? You mean? Okay, okay. Let me find out. So you mean product of two or integer is odd? Is this what you say? Yeah. This is a general statement. Yeah. Yeah. That's fine. I mean, how to say? So if you want to prove this statement, right? You also have to go through this step. So whatever you use, you have to prove it first in mathematics. Okay. So even if you want to like, okay, of course this is a simpler form from this, right? So for this proof, your odd number can be different. So you could have like 2k plus 1. Okay, I mean, you could have 2r plus 1, 2x plus 1, right? But in this case, r and x is the same. Yeah, that's fine. That's one observation. In fact, this is one of the tutorial questions. Yeah. That's fine. I think the observation is good, but to use this, you also need to prove it. Okay. And the way of proving is similar. Just do some modification. Okay. Yeah. Okay. Yeah. Yeah. In fact, this is how you develop maps. So you see some example and then you prove, hey, actually you can generalize and then keep generalizing. Okay. Next. So next we have a proof by cases or exhaustive proof. Okay. So let's do the same theorem. If n is okay, different theorem now. Okay, if n is integer, then we want to show that n squared greater than equal to n. Okay. So always write down what you have first. Suppose n is an integer. Okay, suppose n is an integer. You want to show that n squared is greater than or equal to n. So we want to show that n squared is greater than or equal to n. Okay. So I break the case into three. So whether it's 0 or greater than or equal to 1 or less than or equal to 1. Okay. Typically, when we break into cases, because the group of cases will have similar property. Okay, similar property to show. So for example, when n equals to 0, then 0 is greater than or equal 0 squared is greater than or equal to 0, which is obviously true. And it's obvious. Okay, how about n greater than or equal to 1? Then we can just multiply n of both sides. Okay, which we also get n squared greater than or equal to n as a result. Okay, so both cases we have n squared equal to n. How about n less than equal to minus 1? Okay, then n squared is what? N squared is always positive, right? It's always positive. Okay. And 0 is always greater than minus 1. Okay, minus 1 greater than n. So you also get n squared greater or equal to n. Okay. So yeah. So maybe you will notice that this is a strictly greater, but here is a strictly greater than or equal to. But it's okay because this is an or, right? As long as one of the statement is correct, then the or statement is correct, the disjunction statement is correct. But in this case, we actually have equal case. So when n equal to 0, actually the equal holds is. Okay. Any question? Any question? No? Okay. So the fifth one is an existence proof. Okay, existence proof. Okay, existence proof. So existence proof, I think we actually touched a little bit last lecture. We just found some counter example, found some example for the existential quantifier to works. So let A and B be real numbers with A less than B. Okay. So we want to show that they exist real number x satisfying a less than x less than b. So maybe let's turn it to the predicate logic. So it is equivalent to proving what for every a and b in R such that a less than b, okay, they exist x in R such that. Okay, try spend 2 minutes, discuss with your friend how to find this x. How to find this x. Given you two numbers, how to find a number in between them. Anyone have any ideas? Any breath or breath mind? You got idea? Any idea? Any idea? How to find the x? A plus b divided 2. Okay, good. Let us try. Okay. A x equals to a plus b divided 2. Okay, so you come up with this candidate. So of course I have to check whether it satisfies this or not. So let us try. Okay, try now. So let's try a is less than a plus b. All right. So 2a is less than a plus b. All right. So which means a is less than b. Okay. So this side is okay. How about the other side? A plus b over 2 is less than b. A plus b is less than 2b. So a is less than b. So, okay, so both of these are true based on this single assumption. Okay. So this actually is the working. Okay. So in your real proof, you should uh, write it from, I don't want to say backward or forward, but you need to write it from the assumption. Okay, start from the assumption. So let me put it in blue first. In blue. Okay. So you should say since A B is greater than A, B plus A is greater than A plus A. Okay. So B plus A is greater than 2A. So B plus A is greater than 2A. Okay. Since this, okay, then we have, okay. So similarly, you need to do it for similarly, draw it for what color? So similarly, you need to show it for B plus A or 2 plus B. Okay. Yeah. So you need to do this as an exercise. Okay. So in the proof, usually you start from assumption and then you reach your result. This is our working. Okay. This is just the working. Okay. Any question or not? If not, we break for 10 minutes and then we come back at 10 o'clock. Yeah.
Like the calculus, differential. So it's a bit like the calculus. It's a differential in the calculus. I mean, in the way different the fx equal to the x, and so there must be a value between a and b. So
What are you trying to say? What are you trying to say?
no, I mean, is that similar?
What are you talking about? You say fx?
Yeah.
Fx not
A
equal
function,
to x.
wait, function x is equal x. So
You mean what? X, fx equal to f.
yeah.
And then
There must be a value. So we so x there must be a value between the a and b. I mean, yeah.
you mean intermediate value theorem?
Yeah.
That one is talking about the continue. Let me think. Let me think. Let me think. I think you say you want to use intermediate value theorem, right?
Yeah.
Well, this one is you learn in the calculus course.
Yeah, I know.
Let me think. Let me think how to put it. So you said this is a function, then this is a function that must go through this point. But intermediate value theorem didn't tell you which point, right?
Yeah.
It just says there's a point. Okay, there's a point. Let me think. There's a point. There's a uh, but you see, the problem is this one is R2, you know. This is R inside R2. So my question is on R.
Oh.
So how you turn this question into this function question? You need to figure out where to turn this question into this form, and then you can use this function too. If you can, turn my question into yeah. Mm.
That's a good answer. I just don't know the use of
The use of this everything.
no, that's for fun.
Oh, that's for fun.
It is used to prove something. Like this is a condition in that's right.
Yeah.
Mhm.
Yeah.
So this is a condition.
This is the this is how you have.
We already know this one.
Yes.
So
And then you can get Q. You know these two, and then you can get Q. You get what I mean? So you see, so P or Q, right? Either P or Q is true, then the whole statement is true.
Yeah.
But you already said that not P is true, so Q must be true. Otherwise, this thing is false. Okay.
Thank you.
Hey, why don't you ask in the start of the class? You should ask.
Embarrassed.
No, just ask. Just ask. It's okay. Okay, next time. Yeah.
What's the meaning of this?
This you can throw it away. You can just throw it away. Where you see this?
First, I don't understand what's the difference between this one.
Where do you get this?
Textbook.
Textbook? Can you show me?
Yeah.
Yeah.
all this I don't use it.
Hey, no, you have to show using the truth table. Use the truth table to show. I show one of them in class. You have to use truth table. Did you see the lecture now last week? Last week.
I missed the first link.
Second? How about
Yeah.
second lecture? Do you have the note? Yeah, you see.
I'm just checking this note and not found it.
Hey, where's the lecture two? I prove it in the class. This one. Show that they are logically equivalent. Because the truth value here are the same, so they are logically equivalent. And then the other one you also show like this. Yes. Why you don't ask? Yeah. Okay.
Because in the second class, I missed the first class.
Oh, that's
still checking.
Okay.
Last.
Okay. I mean, why don't you ask in the start of the class just now? When I say if any question.
I'm still.
Huh?
那你还是
You
我
should
跟着
ask
汽
just
车
now.
博士。
Huh?
I'm still at that time following what you are saying at that
You don't know what I'm saying? Yeah.
My English isn't very fluent.
Okay. No, I mean ask in the Q&A section next time. Okay. So that everyone can learn. Okay.
Sorry.
Yeah. So do you know now how to show?
Check the truth table.
Yeah, use the truth table. Yeah. Okay. This one they want to emphasize that you get P first, and then you get Q first, and then you take them together, and this one is all together. But it's not very important. You get what I mean? So I mean this one is just emphasizing that you have P first, and then you have Q, and then you put them together. And then this one is P and Q together. Okay. Not very important, but yeah. Okay. Yeah. And next time ask at the start of the class. Okay. Okay, section. Thank you.
Assume P and assume I can prove that.
Because I like the example, maybe sometimes you can get from not Q, you can deduce not P.
So prove not P from not Q.
Yeah.
Implies the list. Get list.
Because P, because you already know that P is true, right? So anything implies true. Right. Yeah. So you can. Yeah.
I get Q. Why?
Why? Because this is a contradiction, right? So this is always false.
It's false, and only false can
Imply false.
And Q is true.
Yes.
Can I use the function with
How? You mean n times n minus 1? What? You want to find the roots? And to find the minimum is it 0 and 1. And then
I can draw
Yeah, draw. Yeah, and then
find the list food and if I don't go for it to press my interest.
And then what you want to do?
If this is always
I think you can. I think you can. I think you can. Yeah, you can. I think you can. But you have to know that the integer is like split as a subset of R because F is from R to R, right? Are you just looking at the Z? Looking at the Z. So you need to like tell everything. You get what I mean? So,
if this is we can know that the graph above this line.
yeah. So is it the difference here is Z is discrete. So it's discrete. Right? Yeah. So you need to say.
Thank you.
But
So this one is something is one.
yeah,
This one is
this
this is plus
same as this.
this
Is this same as this? I know. Wait, I don't know. I can't decide now. I can't decide now. I think it's different. Different.
So how to prove this one is true?
Okay, maybe not now because I want to start the class. Maybe later. I think okay, later.
Next break.
Next break. Maybe next break. Hey, why don't you ask just now in the 20 minutes class start time? Okay. Later. Okay, later. Hello. Testing 1, 2. I found actually you guys got a lot of questions and you should ask at the start of the class. Actually, I asked the I mean the previous class why they don't ask. They said they don't know how to ask. And then few of you just now say you are embarrassed. Never mind, you just ask. Okay, please ask for the sake of you and the others. And then yeah, so we don't like waste time answering one by one question. Everyone maybe got the same question, then we can straight away solve a lot of save a lot of time. So this last proof is an induction proof. How many? 6 1. So this induction proof, right? I think is very useful for for coding. First, you maybe want to run the loop, so you want to run it for forever. How do you check that it is true always? So you need this inductive proof. Let's give an example here. So let's say you want to add up all the powers of 2. What's the formula you have? It's 2 to the n plus 1 minus 1. Okay. So the inductive proof work like this. So first of all, you check the base case. Okay. So what's the base case here? So the n start from 0, non-negative. So suppose n equal to 0. Then you get 1. Then you add up to 1. 2 to the 0 is 1, which is 2 to the 0 plus 1 minus 1, which is 1. Okay, so this is true. So base case is true. And then, okay, let me write it up. 1, 2. So 2 is the inductive. I call this. Okay, so you suppose the formula is true for a certain number. So let's call k. It's true for n equals to k. Then 3, you want to prove it for inductive step. You want to prove it for n equals to k plus 1. Okay. So you need to check whether or not it's true. So you add it up until k plus 1. So you observe that there's actually 2 to the k hiding inside your summation. So since it is true for n equals to k, then we can apply the formula to the first k term, where you get 2k plus 1 minus 1 plus 2k plus 1. Okay. So what you get is 2 times 2 to the k plus 1 minus 1, which is 2 to the k plus 1 plus 1 minus 1. So this, you see, once you substitute the n as k plus 1, the formula should get k plus 1 plus 1. Okay. And then minus 1, which is what you have here. Okay. So this is the. Now, the idea here is to assume the number is the formula is true for the previous one, and then you prove it for the next one. So the next one is true because the previous one is true. Okay. So what, for example, n equal to 4k is true because n equal to 3 is true. N equal to 3 is true is because n equal to 2 is true. And then you keep going on and you start with the base case. Okay. So yeah, so inductive hypothesis is helping you to jump to the next step. And then you show that the next step is true in inductive step. Okay. Maybe we try another example. Okay. We try another example. So this is proof by induction. So if n is positive integer, then 1 plus 2 and n plus 1 will be 2. Okay. So let's see. So this, we have n is a positive integer, so the base case is n equals to 1. Okay. So let's check whether base case is true or not. So 1 is equals to 1 times 1 plus 1 over 2, which is 1. So base case is true. Okay. Then we need to do the inductive hypothesis. Okay. Suppose it works for all n equals to k. Okay. And then the inductive step is we want to show for n equals to k plus 1. Okay. So let's try 1 up to k plus k plus 1. Okay. So let me check. So when you apply the inductive hypothesis, right, usually we will write by inductive hypothesis. So you must use the inductive hypothesis somewhere. Otherwise. So this one will become k plus 1 over 2 plus 2k plus 1. Why? By inductive hypothesis, right? So this formula, you suppose it is true for k, and then you want to prove it for k plus 1. So your end goal should be like k plus 1 times k plus 2 over 2. So let's see we have this term or not. So since we are adding up the term which can factorize k plus 1, then we get k plus 2. Let's be like. So in general, the inductive proof is induction. Induction proof is you have the base case, and you prove the base case. Usually it's P0 or P1. And then second, you have the inductive hypothesis. So this is assumption, assume PK, okay. Then the next step is inductive step. So assume PK, prove PK plus 1. This is the simple inductive proof. There's other different one. But for this, we will touch on proof. The simple proof. This you can refer to. This is different reference topic. You should refer to Rosen 5.1. Yeah. So we'll add the 5.1 into this section here because this is quite useful. Any question on the inductive proof? This is the last slide for chapter 1. Big one. Any question on this proof here? No? Any question on this proof? Any question on the proof? No? 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 Just feel free to stop me, okay? Okay, let's start with the next chapter. So in this chapter, we will introduce a bit of set theories, and then functions, and then simple matrices. Function matrices. Okay, so let's define what a set is. So a set is an unordered. Okay, we don't care the order as long as it's distinct objects. Okay, there must be distinct objects inside a set. And then we call these object elements. And maybe sometimes they call it a member. Okay. Members of the class. Members of the class. Okay. A set is said to contain, so they contain elements. Okay. Like the classroom contains the student. And then we will write A is in A. So element typically we use a small letter, and then set we use capital letter to denote that A is an element of the set. Okay. So sometimes if you say contain, maybe we'll write A contain A. So the other way around. Okay. So for example, so is Is this a set? Is this a set? Is this a set? Is this a set? No. Why? So because they are same, they got repeated one. Okay. But actually this is called a multi-set. We will go into it later. Maybe multi-set will be more useful in a computer sense. Let's see. How about what's the set of numbers on the clock? What's the set of number on the clock? What number do you have on the clock? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. No, not 13. Okay, not 13. Okay. Yeah. So clock number is actually a modular 12 arithmetic. So we will learn modular arithmetic in the next counting section. Next, 3. So 3 we will have, last time we already introduced the natural number, integers, and then the rationals, and then the real number, and then the complex number. And yeah, we introduced this. Okay. The next one you should learn is this intervals. Hey, I heard you guys took calculus class, is it? No? Or different? Ah, or not the same? Oh, okay. So it's a different course then. Some of you is taking the calculus, but never mind. So intervals, okay, intervals very important. So I'm going to introduce this. So intervals, so closed interval are the numbers in between A and B and include the endpoint A and B. About open interval is the all the number in between A and B, but don't include the endpoint. Why no space? Is okay. Okay, since we have opened, we have closed, we also can have a open interval. Okay, what's a open? There's a close and open one. So I can open one side and then close the other side. Okay. So I think you can guess. So one of them doesn't include A. One of them doesn't include B. Okay, let me see. B. Alright. But sometimes in the book, maybe you will see this kind of notation. Use all the square notation. Okay. And you notice that there actually are two ways to write out this set here. So this is like the roster. They call it the roster method. And then this one, they actually call it using the predicate and truth value. Maybe we'll touch on it again. True value or no, truth set and predicate. Okay. Because usually sometimes we typically when it is infinite, then we won't like list it down. Right? We can't list all of them down. So we found some property just to talk about it all together at the same time. Okay. Similarly, you also could have set of set. Okay. For example, you could have this thing. You could have a set of natural numbers, set of integers, and then rational, and then real. Okay. So in this case here, so the element here is actually a set. Natural number is in here, but 1 is not in here. Okay. Okay. Right. Okay, next. So definition. So we also got a set called the empty set. Okay. Now set. This is the like zero inside your set theory. What's an empty set is? So the empty set is the set that contains no element. Okay. There's nothing inside. So we draw a 0 and then slash. Okay. And then last time actually I told you about the what? The natural numbers. So natural numbers, I said start from 0, right? It's because of the piano axiom. So they use this empty set to construct this number system. So they use empty set as a 0. And then set of empty set as a 1. Okay. Set of empty set and containing empty set and set of empty set is 2. Okay. Can you guess what is 3? Huh? Set containing empty set of empty set containing set empty set and set of yeah. So you like, so what is 0? 0 is actually 0 plus 1, and then 2 is 1 plus 1, and then 3 is 2 plus 1. Okay. Yeah. So all the addition can be built out using this successive function. And then you can keep going. Okay, so this is some short story, but this is out of the scope of this course. So this is just for your information. Okay, so since we got so many sets, so we want to know when are they equal. Okay, like logic, like the logic, we want to know when the proposition are logically equivalent. Okay, 2 sets are equal. Okay, 2 sets are equal if and only if they have the same element. Okay, therefore, if A and B are set, then A and B are equal. If and only if for every x in A, if and only if x is equal. Okay. Then we write A equal to B. Okay. So you need to take every x from A and then show that it is in B, and the other way around, take every x in B and show that it is in A. Okay, let's try an example. So let A be 1, 2, 3. Let B be 3, 2, 1. Are they the same set? Yes. Okay, if you say yes, you have to prove to me. So why are they equal? So you need to take all the elements from A, okay, all the elements from A, and then show me is A in B? Is A in B? Oh, sorry, is 1 in B? Is 2 in B? Is 3 in B? Yeah, okay, you show this direction. Then you also similarly show for x in B have to be in A. Okay, maybe use the other way. So every okay, exercise. Okay. Next. Oh, next this one. So let's define subset. Set is a subset B, and B is a superset. It's called a superset of A. So one is a subset of the other is a superset of the other. If and if for every A in A implies A in B, then we use the notation. For example, for example, the clock number just now. So the number just now is a subset of n. Okay? Subset of natural number. But the natural number is not a subset of the clock number. Why? 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 Huh? So if you say it is not a subset, you need to negate this statement here, right? So if you negate, you use the De Morgan's law, right? So there is for every because there exists. So there exists an A in A such that A is not in B. So why? Yeah. What's that? This one or this one? Yeah. Uh,
I got the answer already.
属于 I think 属于 is this one in Huh? What? 包含 Oh shit, different country Wait, what's going on? What? Huh? Yeah. So you happy already? What 包括 I don't know what 包括 Huh? Now got two things. Okay, there are two things here. This one is an element. This one is a set. Okay, so this is an element. But these two are sets. Okay, so we are talking about two sets here. Okay. 包含 Okay, what's the definition of 包含 Huh? What? Include. But there's no include. Okay. Yeah, okay. Sure. Okay. Include. Okay. So this is a set inclusion. Yeah. Yeah, actually yeah, okay, yeah. And but set inclusion, yeah. Okay, so why n is not a subset of C? Remember the definition of C? 1, 2, 3, up to 12. Why? Why? For example, 13. Okay, so you have a 13 in n, but 13 not in the top number. Okay, so you prove that there exists a such that a is in a, but a is not in b. Okay, okay. Same inclusion. Yeah, inclusion. Okay, so next one, we'll see that this subset is actually not something trivial, because every set X has at least two subsets. Okay, so namely the empty set and the whole set itself. Okay. So proof. So what's the proof? So the proof here will be using the direct proof. Okay, we use the direct proof. So we need to show. We want to show that phi is in X, is included in X, and X is included in X. Okay. So how to show? You need to go back to your definition. So to show that phi is a subset of X, we need to show what? We need to show for every X, okay, X in the empty set implies X is in the set, right? See? Right. Tuck it in. Okay. But does empty set has any element? No, right? So this statement is true or false? False, because there's nothing inside, right? So this statement is false. False implies everything. So this statement is true. Okay. So let me spell it out. Since P has no elements, okay, X is in V is always false. Okay. So the conditional statement is always true. Okay. So in this case, we have a technical name for this kind of situation. We call the statement is vacuously true. Okay. Vacuously true. Vacuously true. Okay. Vacuous, nothing inside. Okay. So can you show the other one? Can you show exercise? Show axis. Can you show this yourself? So you have to show that what? By definition, you have to show that X is in X, implies X is in X. I'm repeating. So, right. So can you do this? Okay. Since this is true, then this to be true. So everything true. Okay. There's not much to do, but you need to know what's going on. Okay. Any question or not? Any question or not? No? Okay, next. Oh, not quiz yet. Okay, wait. Not yet. Still got time. Okay. Keep going. definition. Okay, so I can make another definition. I said that A and B are equal. Okay. Remember, we write A equal B, right? Okay. If A is a subset of B and B is a subset of A. Okay. So you can show that this definition is equivalent to the previous one that I gave you. So the previous one, I said that if only if they have the same elements, right? So you can show that these two are actually equivalent. Okay, so you can go from one definition to the other definition, and then go from the other definition to the other definition. Okay. Okay. Okay, next we say that okay, now we introduce a proper subset. Proper subset. But I don't know what's the Chinese word for this. Proper subset. Okay, you can see what am I writing, and then you can decide what you have learned. So proper subset is if A is a subset of B, but A cannot be equal to B. Okay. Or equivalently, okay, for every x in A implies x in B, and there's this x in B, and x is not in A. Okay, so we will write. So we write. Sometimes people write A subset of and then slash the equal signs. Okay. So for example, okay, maybe you want to study how the numbers sit between each other. So remember the quote number is sit between n, and then sit between z, and then sit between rational, and then sit between and then sit between c. Okay. So this is how the numbers sit inside each other. But actually, right? Still got time. So actually, in your okay, maybe I ask you a question. So have you wondered why the number line you draw like this? Why it's drawn as a line? Like in your function, why you draw as a R to R as a plane? Why? Anyone ever wonder this? Wonder why you can draw as a line? Anyone thought of this? So when you're counting, right, the number actually there's a fixed distance between them. So it's like 1. Okay. Like every entity of you, you have distance between your friend, right? Yeah, not stick together. Right? So for example, this 0 and 1, they are one length away from each other. Okay, one from each other. Okay. And then we start getting closer. Okay, we can divide things. Okay. We can divide things. And then we can go the other direction as well. So we got 2 directions now. Okay, going backward, going forward. And then remember we proved that any between two real number, we can find another real numbers. So we can keep filling in the space. Keep filling in the space. Keep filling in the space. Okay. And then keep filling in the space. Until we can show it actually is a line. Yeah. Okay. And then show it is a line. And then for C, right? C actually we have this I and then this minus I the other direction. So actually we can see that C is actually cross. Okay. So in C, actually, there's different copy of R. So maybe R can go this way, can go this way. So there's a lot of R sitting inside C. Different R sitting inside C. Yeah. Okay, never mind. Yeah. No, I mean this, I think this is more interesting. Yeah, this is like the topology of the number. Yeah. 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 Okay, never mind. Next. Well, you want to do quiz now, is it? Okay, just keep going first. And then we'll see. You want to keep going, or you want to stop here, or you want to stop here? Okay, I'll stop here because previous class was actually, okay. Actually, previous class how about one interesting concept that I can share with you about this proper set. So actually, I haven't introduced them a proper set, but maybe they're learning somewhere else. So they asked me a question: What are the proper? Which you also can think. What are the proper subset of an empty set? What are the proper subset of an empty set? What's the proper subset? Maybe will become a quiz question. Not today. I mean, not today. Not today. Today is the logic. Not today. I mean, the next one. What are the proper subset of an empty set? Yeah, maybe you can think. Yeah. Any question on the previous lecture, or you want to discuss this? If not, then maybe you can break earlier and then we come back for quizzes. So we break until 10:55. Okay, break until 10:55, and then come back for quizzes. Yeah.
Yeah.
Oh, you can do that.
Hello. Can you sit down?
Okay. Actually,
You use my iPad? Okay.
can. I mean, actually, wait. I mean, oh shit! You huh? Yeah.
What's this?
What do you mean?
What this?
Uh,
I saw he that was cute.
wait. Oh, wait.
Yeah.
Huh?
This.
Oh, this one.
Oh yeah.
Then this one. Then I also write it here. Actually, I think you guys also forget, so write it here already.
Go.
Plot number. Then here. This one.
Oh.
Actually, I also write it here.
Oh.
Right here. Yeah. Yeah.
That's all. This one.
Okay, let me check. Let me check. I think last time I gave wrong statement. Okay, not yet. Right? Oh yeah, right. Okay, this one correct. Okay, yep. Yeah. I prove this one is a tautology.
Yeah.
So
How to prove?
how to prove?
Yeah.
No, tautology is you can prove using the two way to prove. one is use the truth table. You know how to use the truth table? Okay, so you write everything out and then you show that this compound statement is always true. Second is you use algebra. So when you use algebra, you need to show that this is logically equivalent to P. So it's true, always true. Two ways.
For truth table is
Yep. Just
for anything can use.
give me everything.
If I want to prove all this
Uh-huh.
kind of question, I can use truth table.
You can use truth table, yeah. Yeah. Yeah.
So is this graded on
Is what?
the quiz?
It's quiz.
So is it graded on
Graded
graded like for the
assessment.
yeah?
Yeah. Why?
Because to be honest, 2 days ago I just come.
Oh, you just come
Then I
Okay.
just got my first probably 11 p.m.
yesterday.
Yeah, so I'm not sure.
I'm not sure you can do or not. Or maybe okay. You maybe you try and then I see how's your result. If it doesn't work, then maybe I consider just take average of the other quizzes.
How about the previous quiz? The one that I got the 10 to.
No, just this one. This is the first one. This is the first one.
Oh, this is the first one.
Yeah. Yeah, if this quiz you can't do it well, maybe I just don't take it. I just take the average of the other quizzes.
Oh yeah, the quiz we also take it on paper, right? We write it on paper.
Yeah. Is that okay?
Is that
What's your name?
adjective?
I think I yesterday I just said one person. William. William. Okay. If you can't do well, then maybe I just don't take this one, and then I just take every of your other marks. Is it okay? It's okay. Okay. Thank you, sir. Yeah.
We can understand this.
You can understand this?
We don't know why this will and then
Okay.
Mm.
Do you know? You don't know why this? You don't know why this implies this? Or what?
Yeah.
Okay. So here is a tautology. That means this compound proposition here is always true if you do the truth table.
Yeah.
Okay. So this tells you that this statement here is always true.
You should remember it.
Remember it? Don't need. You don't need to remember it, but this one is kind of how to say. It is natural because you know why? Because if you have P and Q, if you have P implies Q, and then you have P, of course you want to deduce Q. You get what I mean? So you got a statement P implies Q. I tell you that if you have P, you will get Q. So if you have P now, then you will get Q. You get what I mean? You get what I mean? Right? How about this? So this is because P implies Q is logically equivalent to not Q implies not P. So now you have not Q, then you can get that. Yeah. So that's why I write contrapositive here. So what's the contrapositive of P implies Q? Yeah.
This y is 2 square and equal to this
Oh,
where
on here. Yeah. 2n square. Okay. M square. M square is 4n square.
oh
Yeah.
Thanks. Wonder which come from. I only have square and
Yeah, because lemma, since a number square is even than the number. Okay. Yeah. Because this is true for any m. So you can apply on m.
it is
Then
because only square and
if n square is even, n must be even. So okay. So this statement here is true for any integer, not just n. You understand?
I understand.
Okay.
I don't know how to input.这怎么重新回到这个？
用这个。
这个对所有整数都是成立的。它会仅对不对称的都是一个正确的，不对的是它对不对称的一个动静。这是你的问题。
对，问题是
这个是怎么证明？方
那你为什么懂这个？然后你有没有这个是证明你？所以你懂不懂这个？
这个不是最后理解的东西，然后
嗯哼
这个东西得到这个东西我理解，但是这个东西它本身是怎么得的？
你是说 n square 为什么是even？
就是这个本身是从哪里来的？因为电脑过程中我没看到很多，然后这个就方，或者
因为我可以从这个 n 方得到。什么意思？我听不懂你这边。就是因为你说 OK，你现在的纠结点是怎么从平方变成没有平方嘛，对不对？
对。
但是这一句话告诉你怎么从平方去到没有平方嘛。所以你明白这句话吗？
这个是要证明。
对呀、要证明啊，所以又怎么样呢？跟你明白这句话跟要不要证明这句话是没有关联，这两句话。第一，你一定要明白这句话在干嘛先，然后我们才去证明。关于要不要证明，跟你理解不理解这句话是没有关联的。所以你不理解这句话，你理解什么？嗯哼。所以它是不是已经有一个桥梁从平方到没有平方？有没有解决掉刚才你的纠结？所以你的纠结点在哪里？我现在不知道你在哪里纠结，所以我不知道怎样帮你。你再想一下。嗯哼，对。
但是为什么我们要证明这个东西它确认，因为就可以直接跳到这个什么？是这个意思？不是
啊，不是，我也是觉得不是，但是我不知道你的纠结在哪里。再问一下，你再想一下，猜一下，我们慢慢猜，应该有很多东西藏在一起，我不要慢慢猜。你再想一下，你想问什么？对。但是我想跟你说的是，为什么我可以说这句话，是因为这个简单，就是为什么我写这个，因为这个。然后你再看哪里你不知道，还是你不知道这句话什么，或者你不知道这句话什么。
所以我东西是偶是死的，因为那个条件一是那个一是那个是负的，在此是这个是怎么样？
所以你想问的问题是 n square 为什么是 even， 对不对？因为我只要知道它的平方是 even， 我就知道它的那个叫什么 square root， 它的 square root， 平方根就是 even。这个是这句话说的，你只要知道，你一知道它的平方是 even， 你就知道它取根过后它就是 even。
这句话是不需要证明的。
这句话哈，这句话对不对？要证明，要证明。
是吗？证明这句话是这样的。
没有，我只是用嘛，用这一个，用这个事实，这个事实是要证明的。对，我证过一次。对，用反就是叫反证，用 controversity 啊，其中用反证。
对，已经证明为什么要用反证？是我这个例子是用来做什么？
OK， 用来，因为我说 m 和 n 不可以有 common factor 啊呀，对。
我那我回去忘掉，我拍个照片拿回来。
对。
等一下，
没事，你再想一下，你再想一下。你管我，我会那个。
我怕我回去就忘了，我得把它。
OK， 对。啊，不会。Okay, please turn. Hello. Please turn off all your electronic devices. Close down your laptop, and then turn over your screen. Yeah. Switch off your laptop, and then put your phone, the screen down. Put your screen down. Okay, and then I need okay, we got 4 rows here. We divide into 4 rows. And then the first person in the row, please help me count how many students in your row. And then come and collect the quiz here. Okay, you tell me what's the number in your row. 9. Okay, you collect 9. No. Just one is enough. Just 4 rows. 8, right?
18.
Oh, 18. Okay. 9. 18. Okay. 14. 14. Okay. 14. Okay, you can read, but don't start first. You can read the question, but don't start first. Ah, 19. Okay, you can read, but don't start first. Which 32. 60. Okay, you can read first, but don't start first. And then in case you don't know what the word I use, it's just 2 restaurant, but the restaurant is not very important. Important is the proposition. And then there's some typo because I initially got some. I would say. No, I would say no. Yeah, we will finish it within the time. Yeah, no worries. Yeah, this is a short, we will take 15 minutes. Wait until everyone get first. You can read, but don't start first. Uh, okay, wait, listen to me first. Okay, so there's definition, I put it here. There are two restaurants that I put inside my question. And then there's some typos here because initially got longer question. And then task 2, I want you take note here. I want you to prove it is a logically equivalent using a truth table. And then question 3, 1.3 is 20 marks. And if you leave this room, then you forgot the problem. You don't go and spread the problem because there are students that haven't taken it yet. Okay, now we start 1102. We will end at 1117. 15 minutes. Start now. The honest policy is you're honest to yourself. Don't cheat. I believe you. 3 more minutes. Please write down your name and student ID. Remember the last minute. Okay, if you change your seat, please click back to your original seat before the quiz is given. And then now check your name and student ID, is it written? And then pass it to the front. The first person that help me to count the person, please count whether you have the right number in your row. Pass to the front.18
我想问一下，这句是啥意思？
就是说要 creative
有创造力的
啊，
有创造力的。这个是举一个例子就行。
对，
举一个例子就行。那这个是
没有，这是1.2
啊
1.2，我是说你可以用不同的东西，17、18，就用不同的 if then 啊 and 啊 or 啊，可以做一个 proposition 嘛，对吧？14啊，好，等一下，等我算好先。Nine. Huh? Why is it wrong? Huh? You're from this group. How many? You got 19 or not? Now you got 19? Now you got 19. Okay. Okay, you can continue with the tutorial question and then we will do discussion at 11:35.
Later I show to you. Later I can show you guys.
Hey, who wrote Chinese name? I only have your English name. Why you wrote Chinese name? Huh? Hey, quite a few. Oh, you want to check out? Never mind. You got ID. Okay. Okay. Officially here we use English name and ID. Okay. Next time, please don't put Chinese name. Okay. I only got your English name only. Since you got ID, I can check out. Next time, please use English and not Chinese. I mean ID. Also, I have a DMT class. Write Chinese answer. I tell you straight away 0. I tell you, I can't read. Okay, hello. You can keep going with your work, but I found some interesting solution here. In terms of quantity, yesterday have more, but today quality is better. So let's see. The one saying, when is the proposition you made just false? Okay, the one, this one is the usual one. KFC drumstick is better than Mamak's. Okay, is that when someone thinks Mamak drumstick is better than KFC, then the proposition I just made is false. Yeah. So no need someone thinks. Just say that when someone is what is better than the other is false. And then this one also, when is the proposition you just made false? When an Indian Muslim who doesn't like fried chicken comes to this school. Wait, we are logic class, no, not the survey class. Logic class. Okay. Wow, this one very good. Or this one QX or RX FX. Wow. Everyone who had been go to KFC and Mama, KFC is better, Mama is better. So what? So you want QX imply RX. So QX imply RX. If everyone who had been go to KFC, KFC is better. Wait, no. You say that if for everyone who have been go to KFC and Mama, do you want to say things that KFC is better than everyone? Well, I don't know. Too complicated already. Don't know how to put them together. The first. Okay, I think this one is pretty good. If KFC's drumstick is better, okay, don't write is better than Mama, then Kisen will go for KFC drumstick. Wait, but you spell my name wrong, so you get deducted. Okay, I think this one, well, this guy maybe know me well. Huh? See, okay, the indication is correct. Correct or not? When maybe wrong ones, I don't know. Okay, the next one. If you prefer to Indian cuisine, Mama's is better than KFC drumstick. Wow, this one quality. This one very quality. If you prefer Indian cuisine, Mama is better than KFC drumstick. So if you prefer to Indian cuisine, but KFC drumstick is better than Mama, then the proposition I made was false. Well, this one very logical. This one's logical. Okay, very good, very good. Oh, I know why you spell my name wrong. Your name also got Seng. Okay. Okay. You want to discuss now or not? Yes, okay, just discuss now. I mean, not discuss the quiz problem. I can't discuss it now because still got student haven't take the quiz yet. Okay. So 1.6.20. If x is a positive real, then s squared is a real. Implies that if your s squared is real, then a is real. This is false because the inverse, not inverse, is this inverse? No, this is not inverse. This is what? Converse. Converse. So converse is not logically equivalent to the original position. And then the next one is if s squared is non-zero and x is real, then s is not zero. And then the other one is if x is real, a is real, a squared is not zero, then a is not zero. So this is true. They implies each other because you just swap, just use commutativity, swap the condition. Okay. 1.6.24. We already showed that last week these two are not logically equivalent by providing an counterexample. So here they attempt to prove it. So something wrong with the proof. So it's inside here 3 and 5. Because you cannot deduce anything from a disjunction proposition. Okay? Only conjunction you can. If this is an N, then you can deduce PC or QC. Okay, or you cannot deduce anything. Okay, or you cannot deduce. So the next one is 1.6.28. This one have a few ways to go, maybe 2 ways to go about. So one way is to keep this and then use the algebra, keep going until you show this. This one I use is similar actually. This one I use the instantiation and then use the law together and then to break, turn the implication to the disjunction and then you do some algebra as well. Similar algebra actually. Just that if you use the full algebra, you just keep your quantifier. But now I use the instantiation here. Okay. Instantiation. Okay. and then all the way down, and then I put the generalization back. The last step I put generalization. Okay, you should try it out, and then I will put on this solution, and then you should check. And then if you have any question, you just bring to the office hour. And then also math help center, and next week lecture you can ask as well. There's a lot of chance for you to ask questions again. Completion. Okay, yeah. So this one mentioned by your classmate just now. Prove that the product of two odd integers is odd. Okay. Also, you can prove it for even integers. Prove that product of two even is even. Okay. So this one is just direct proof. Direct proof, you just need to know what you have first. Okay. And then what you want to compute. And then you show that actually this is an odd number. Okay. Turn this into an odd number. Turn the product into an odd number. This is the only step you need to think about a little bit. Okay? Think about it. Okay. Next one, prove that if n is an integer and s3n plus 2 is even, then n is even. So actually, so I will produce two proof here. So the textbook also asks you to use two kind of proof to prove it. So also, if you look at this proof, you should be able to decide which one is contradiction, which one is contrapositive. Okay, just by looking at the proof, reading the proof, you should know which type of proof I'm using. For example, this one. See, I start with what? I suppose n is odd. N is the result, right? So this is a not Q. Okay, and then start from here, I get that not P. Right? I show that 3n plus 2 is odd. So this is actually a contradiction. Okay. Sorry, contrapositive. Okay, because I start from not Q. Okay, and then I end with not P. Okay, but for the next one, you will notice that I got supposed two things. Okay, one n is odd. Okay, which is not Q. The other is 3n plus 2 is even, which is P. Okay, so I start from not Q and then P. Then you should know that I'm trying to do contradiction. So you see, and then I do the contradiction. Okay, just do the same calculation, and then you see that, hey, you got not P. So it's a contradiction. You got P and not P, contradict. Okay. Okay, next one. So prove that m squared equal to n squared if only if m equal to n or m equal to minus n. I included this because this is a statement of if and only if. So you have to go forward, and then you also can go backward. Okay. So I claim that backward is easier because you just use what you have and then you square it, and then you automatically get what you want. But the other case, you need to do some clever trick, maybe factorize it, and then you will see that m is actually equal to n, or m is equal to minus n. Okay. So one direction, the other direction, both directions you need to show. Okay. Okay, 1.8.2. Show that 10 is not a square of positive integers by cases. So how to do by cases? So you should notice that there are numbers that square to square, which is less than 10, and then the others are greater than 10. Okay, these are the two cases you consider here. So two big cases. Okay. And then 1.8.16, prove or disprove that if A and B are rational numbers, then A to the power B is also rational. So this question, proof of disprove question, is sometimes a bit hard because you need to convince yourself whether it is true or false, right? So if you just think around the true, maybe there's a false, then you are wrong. Then so sometimes you need to be a bit creative. So for example, in this case here, so I prove to you that square root 2 is irrational. So even though the power is rational, the base number is rational, you take the power is irrational. So this is false. Okay. Okay, one point, the supplementary 38. if a cube is irrational, then a is irrational, right? So first thing going through your mind is what? What's the definition of irrational? I only tell you what's the definition of rational, right? So you should go from the definition of rational. But to use rational, there's one way you can use that can let you use rational is to assume not Q, and then you prove that not P. Okay, it turns out it's easier, right? So if you assume A is rational, then you can write it as a ratio of integers. And then you take the cube and then you just multiply the ratio together. You still get a ratio form. Okay. So show the contrapositive. Next, 5.1.16. Okay, you want to add consecutive number integers together. 1, 2, 3, 2, 3, 4, 4, 5, 6, 2, 3, 4, 5, 4, 5, 6, and so on. Then we got a formula here. So first of all, you check base case. Base case is n equals to 1, right? You sub into n equals to 1, and then you check whether this formula is the same or not. Okay, base case done. Inductive hypothesis, assume this is true for some k. Okay, and then you want to show it for the next k plus 1. So you put k plus 1 in, and then you realize that inside this term you got k term, the k term, then you apply the formula. You apply a formula and then you combine the terms, factorize, and then you get the k plus 1 formula you want. Okay. Right? Okay. So this is quite similar to the class example. But the next one is a bit different. So you prove that 3 divides n cubed plus 2n, okay, for every n. So how to use induction? So when n equals 0, anything divides 0. Okay, so in particular, 3 divides 0. Okay, and then suppose it is true for n equals to k. You want to show for k plus 1. Okay, so you put k plus 1 in, and then you see, seems like there's nothing k terms exist here, right? So you try expand it first. Okay, expand so that you can get some k cube, something like that. So you expand first, okay, and then try and find the k term because you need to use the inductive hypothesis, right? So you need to find the k to the 3 plus 2k. Okay, so you found, I found k to the 3 plus 2k, and then the other rest is like this. Okay, so this part here by the inductive hypothesis is divisible by 3. Okay, so it's 3 times something, and then the rest is every one of them have a factor of 3, so it's also divisible by 3. So the whole term is divisible by 3. So the k plus 1 term is also divisible by 3. So done. Okay. Yeah. So which question do you want me to go over again? Which question you want me to go through again? Yeah, you have to try first and then you can compare the solution with me after. I think I will put it up today later even. Any question you want me to go through again? Mm. Any question you want me to go through? And just now you got the question, is it? Oh no, not you. Okay. The other one. Oh, never mind. Okay, that one is solved already. Any question that I haven't solved just now? Someone come and ask me. Have you? Are you okay with the question just now? Huh? You okay already? Okay, maybe I touch on this a bit. So if I first time learn, I also will confuse on that point. Like, okay. So because this one statement I wrote M here, right? Actually, it's not this specific M, okay? This M here, actually, I can change to A, B, C, anything, okay? The most important thing is, notice that I go from a square term to its roots, okay? So I can know what happened to the roots by knowing the square, okay? So if the square is even, then I will know the root is even as well. So because this n square is just some other square term, right? So since it is even, then I can apply this. Yeah. So maybe it's my bad habit to use m, but in mathematics you need to um, sometimes you need to know where is the abstract one, where is the specific one. Okay. Yeah. So in this case, here is the abstract m. So actually, I can change this to like a square, a, and then here a square. Okay. So yeah. And any question? Any questions? Any question? Any question? What about this question here? Anyone thought about this? Huh? What? None is what? None. So the answer is none, or the answer is none, or what? The answer is none. Yes. So there's no proper subset of an empty set. So in other words, the set of set of an empty set is an empty set. Then you can prove this. Prove it. Okay. The set of proper subset of an empty set is an empty set. Any more questions? No more? No more can dismiss. Oh, wait. Before you guys go. Hey, hello. Very important, very important. Warning. After you leave this class, forget the quiz problem until I give you back. Forget the quiz. Cannot discuss outside this room.
There is a distance between the A and B. If I prove that there is a distance
Okay, thank you.
between the A and the B,
Yeah.
then I will prove this.
But you prove what's the distance? But how why the distance? Why inside the distance must have a number? Why there's a number inside the distance? Why must?
I think there is must be.
I know there's a yeah, that's what I want you to prove.
I need to prove.
Yeah, you need to prove.
It's highly different there.
Yeah.
Thank you.
Yeah.
So where can I see the answer of the quiz?
Where can you see the answer of the quiz? Or after I give you back the quiz, then we will discuss.
Okay. Actually,
Huh?
I don't understand stuff. This three step.
This three step.
Can you explain again? Can you explain again?
Can you explain again? Okay.
This three.
You mean all of this?
Yeah.
So, okay. So this one, so this statement is true for all n. So I need to prove for every n. So you have to check for every n equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, everyone.
Yeah.
But you can't do it all of them, right? So you do use this induction proof. So induction proof, first you prove the base case. So it's the first one that appear. You prove that first. So this one n equals 0 is true, then okay. Then second, you assume that certain k is correct, and then you prove it for the next k plus 1. Okay. Okay, then you just do this, what I do here, and then show that it's true. And then why this show that everything is true? Because the fifth one is true is because the fourth one is true. The fourth one is true because the third one is true. The third one is true because the second one is true. The first one is true. The 0 is true. Because 0 is true, right? So imply everything is true.
Oh.
Yeah.
So, for this. Actually, I cannot understand this.
Oh, you cannot understand this. So you see, so so you see that this part is actually the k part. So 1 sum to 2 log k is you can apply the formula here because you assume this part is true. You assume this part is true, then you apply the formula. Okay.呀，很多不懂，为什么刚才不问啊？该问，可以问，不用紧，问吧。
老师说的每句话我听得明白，
你要听明白，
连在一起就不明白。
恐跑了就不明白。什么？every positive real number has exactly 2 square root。所以呢，怎样？
这个答案也是看不懂。
哦，你是说要怎么写哈？所以 ，OK， 你就他说 every positive real number 嘛，所以你就说 every positive real number 是大于0啊。OK， has exactly 2 square root， 知道什么意思吗？就是说，there is a unique， 因为我只教过你一个东西是 unique 嘛，但是他现在要跟你讲一个 unique， 他不是但我 try 一下，我写这个啊。
因为我自己答案也是写 unique， 但是我看答案就不错了。
或者
是 exactly 2跟 exactly 5。
我知道，我想说的是 exactly，OK， 我试下写两种东西出来。So exactly 有一个，然后 exactly 有另外 ，OK， 我试下写两种，看一下有没有 match 到你的答案。所以 actually 这个 exactly square root 啊。OK， 或者他是写的 this y not equal to z， 他这样写，他写 not 哈。
我看得懂。
not 你讲哪一个是他的答案？C 哈，对，他是写这个咯，他是写这个的 version 哦。OK， 然后他先跟你说这两个东西是不一样的东西，然后每一个 C 啊，他 introduce 很多东西进来了，给我想想啊，他这个很啰嗦，因为他为什么啊？他又把这个东西，他先告诉你这个东西是一个东西的 square， 然后这个东西可以等于 A 或等于 B，看你怎样写啦。你有没有你自己的答案？我可以看一下你的答案对不对？因为它这个是很啰嗦的写法，你要跟也是可以，但是不要跟也是可以。像我这样写也是可以的。
这样子。
你就，因为我把这个我没有在 introduce 这个 C 的东西啊，我就直接这个是不太好的。你要写它的 domain 在哪里最好。我在课上，对对对，我在课堂教的都是有，我下次再提醒一下兄弟。所以我每一次我写，我都要写这个东西在哪里，所以我会写，可能我就这样写了。There's this，有想一下啊，因为它要 exactly to，有想一下啊，
考试不会出这样的。
考试哈，应该不会耶。
因为答案没有给到 unit 的事是。
什么时候？
讲不一样。
他答案没有 unit 的事。
啊，对，没有原因的，因为可能它的原因就是因为它来 introduce 这个 C 了，因为它是说 C 只可以是这两个吧。但是如果我有 unique 的话，我就说，就我也，你懂什么意思吗？就是怎么讲呢？我就，OK，我放了 unique，我可以代替这个东西。
这整个。
对对对对对对对对。但是如果没有 unique 的话，如果你只 OK，这样我们讨论一下这个有什么问题。所以 there exists y 跟 z such that such that y square 等于 x 等于 z。这个很
y axis
OK OK OK，我应该要这样子写，我应该这样写比较好。y in r，然后我应该要写，不是我写 z，然后 n，但有一个问题是因为它不 exactly 了，就可能有多过两个不同的东西。对，但是他要表达是 exactly，所以他要说有一个东西 square 去 x，但是那个东西哦只可以是 a 或者 b，这个是他讲的，可以明白吗？可以吗？还是有点乱，还是乱，还是乱，还是乱了啊？OK，你要看这句话，每一个 positive real number has exactly two square root。你看是什么意思？你讲一下。只有两个号码可以 square 去它，对不对？啊，对对，只有这两个 square root 可以 square 去这个 real number，square 成这个 real number，对不对？
啊，对对对。
所以意思说，如果有一个号码是可以 square 成这个 real number 的，它只可以是这两个的其中一个，对不对？啊，这句话是他讲的。
所以答案
哪一个？
其实
不是这个为什么不可以？我想跟你说，这个为什么不可以？因为我只想 there exists 这个 such that 它们不等于，它可以有四个啊，也可以有四个可能性啊，也可以有三个可能性啊，但是它要把它可能性缩到只有两个。
这些老师如果改这种题目是没有正确答，没有真正的答案，对吗？
不是讲没有正确答案，就是它可能有不同的答案。
所以老师改的不是看那个 scheme 对吗？
你讲这个的 scheme，我自己的 scheme 啊。
如果有这种题目的话，老师也不是真正照着那个 marking scheme 来改的，对。
不一定，除非你写的东西就是
完全不一样，除非对吧？
就是你如果写跟他不一样，但是你的意思是一样就可以，对，明白吗？写不出啊，就至少要写一个东西我才可以检查哦。但是我觉得呀，没有了，就这样。我没有 stop 啊，等一下。